Okay, it's time to begin now that Russell's here. And I have everyone here but Tioni again. Hopefully he's feeling better. Okay, this is the slide that didn't show up. Remember last night there was one slide that it was blank? This is the one. It was showing us an example of a lunar calendar. In this case, it's the, I'll try to pronounce it, Hijri. Must be feeling better. There's Tioni. The Hijri or something like that, the Islamic calendar. There are actually a couple different variations of the Islamic calendar. Because this is not on the day that I had created it for, it's no longer the 23rd. In fact, I think that was Monday's date was the 23rd, so today's probably the 25th. I didn't re-look it up. But we're in the month of Dhul Qa'dah, and every new moon, you start a new month. And actually, their months, I found this interesting, each month has special things about it. So, for instance, war is banned this month, but people are allowed to defend themselves if attacked. So, people who follow strict Muslim beliefs during this month period, they won't attack anyone, but they'll defend themselves if they're attacked. Next month, Dhul al-Hijjah is when the Hajj occurs. That's when they take their pilgrimage to Mecca, and war is banned. Likewise, in the first month of the year, the one after that, all fighting of any kind is banned. Now, of course, when you're at war, you probably aren't going to stand with these. And I'm sure ISIS views themselves as at war. So I'm not saying that, there's not going to be any kind of ISIS activity during that time period. But it's interesting to see that, they call it the religion of peace. And you can see they at least have some months where they very much do specify peace. But the key about this was not looking at their piece, but looking at how the calendars compare. If you're going to use the Islamic calendar, that's fine and good, but you also need to be able to communicate with people who aren't if you're not living in the Islamic world. And so this is an example where it just shows a month with the normal calendar and with the Islamic days on it. So you can keep track of them. So that's what we missed last night in the slides. This is the one I ended on last class period. There was a new word on this. I'd used it earlier, but it was technically first came up here, that word. Hannah, you do have an answer in, but the question hasn't been asked yet. Actually, she's answered more than once. Just got to make sure. Actually, I guess, does it tell you what the question is? Mm-hmm. Oh, okay then. So it's not just an ignorant answer. Elongation is the angle between the sun and the planet. So for most planets, for all the superior planets, they can go all the way to opposition, which would be an elongation of 180 degrees, right? The angle between the sun and the planet is 180 degrees when you're in opposition. But inferior planets can't go to opposition. And so elongation is the biggest angle you can make between the sun, the earth, and that planet. So just to make sure we have another word, when something's at quadrature, what would the elongation angle be at that moment? 90 degrees, right. Because quadrature is when it's 90 degrees, sun to earth to the other planet. We'll see in a slide coming up that, actually, I think it's the next slide, a variation on quadrature for inferior planets. So Mercury's greatest elongation is 28 degrees. Doesn't get more than 28 degrees away from the sun as viewed from Earth. And Venus has elongation of 47 degrees. Doesn't get farther than that away from the sun as viewed from Earth. So it's pretty clear they aren't going around the Earth. Or excuse me, I shouldn't say it's pretty clear they aren't going around the Earth. It's pretty clear that they have to always remain reasonably close to the sun. And so when Ptolemy modified his Aristotle system, and we'll see a picture in the second clicker question today that really illustrates it, he ties Mercury and Venus to the line going from the Earth to the sun so that they will remain within the confines of the maximum elongation that they can have. So let's talk about Nikolai Copernicus. Nikolai Copernicus, or you'll see his name written different ways. Nicholas, it depends on what language you're actually using. So this here, I think I said, Nicholas Copernicus here. He was a Polish canon, if I remember right. Hence the stamp here from Poland. And correct me where I make a mistake. He was the person who came up with the idea that the sun is the center of the universe rather than the earth. Where was my mistake there? What?
Do you think the earth was the center and not the sun?
No, he did think that the sun was the center.
The sun is the center of the galaxy.
Not galaxy, actually. The solar system.
Yeah, solar system.
Okay, so that was one error. That's not the only error in what I said, but that's one error that he had. Back then, people thought the universe was all about us. And so they thought that the earth was the center of the universe. And then he was suggesting, no, it's not the earth that's the center, it's the sun that's the center. We're just really darn close. But there's another thing that was wrong in my statement. Yeah, he wasn't the first. He was more like the last. Right? Before him, we had plenty of people. We talked about, was it Eratosthenes? No, it was, starts with an A. No, the one we talked about between Aristotle and, I can't remember his name. The one we talked, Aristarchus, yes. Aristarchus, I believe, is the one who proposed that the sun was the center and everything was going around the sun. Archimedes, now I'm really. Aristotle had said that the earth was the center, and I'm not going to say names not in English today, it's just not working for me. Aristarchus proposed, no, I think we're all going around the sun. So the idea of going around the sun wasn't new with Copernicus. It had been around for a couple thousand years. But Copernicus was the last one to reignite the idea before it was accepted. Notice before it was accepted. It wasn't accepted when he said it either. So what did Copernicus do? Now, first of all, part of the reason it wasn't accepted during his lifetime is because he was a Polish canon, which is not a reference to Sebastian Janikowski, but rather a religious title, the canon there. He worked for the church in Poland, and his ideas ran counter to the Catholic Church's understanding. Now, the Catholic Church had developed a theology to explain what was really Aristotle's idea. We know that in the Bible it talks about the heavens above and going down to hell. And so the Catholic Church adopted the idea that above us is heaven and below us is hell. And Aristotle had believed even that everything out there in the heavens was perfect. That worked great for the Catholic Church. So everything out there is perfect because sin hasn't entered. But down below, we have sin here on earth, we have hell down below, it's bad. And so the church kind of wanted to maintain this idea, and people who taught differently were heretical. And so, being a firm believer in the Catholic faith, he did not want to preach heresy. He did write out little handwritten pamphlets that were anonymous, and he would hand them out to people. And finally, at his death, he finally allowed his ideas to be published with his name on it. Then he died, didn't face any repercussions. But what were his ideas? Well, they weren't just founded on wishful thinking. He did some measurements. As I was preparing the lecture this morning, I sat down with pen and paper to make sure I could do the same geometry he did. I came up with my equation that I could relate the time between opposition to quadrature or conjunction to quadrature if it's a superior conjunction for an inferior planet. And I can use that. I figured out my equation to determine the ratio of the radius of the Earth's orbit to the ratio of the planet I'm observing's orbit. That's what he did. He did that little geometry, came up with an equation so he could just take the time between conjunction or opposition. Notice this picture here is going to have opposition, not conjunction. This one here has a superior conjunction. So over here where it just says conjunction, it depends on if it's a superior planet or an inferior planet, which one it's going to be. For the superior planets, it's opposition. For the inferior, it's the superior conjunction. And then it has to quadrature. Now the quadrature, as I explained it, is shown in the opposition picture. Right? The angle from the planet to Earth to the sun is 9 degrees. But for the inferior planet, it's the quadrature for the planet observing the Earth and the sun. Because you can't have quadrature by the normal definition for an inferior, only for a superior. But at any rate, he just measured the time from when they were lined up, so the time from starting here until the time that it gets to these two positions here. And measuring that time, he was able to calculate the ratio of the radii. And you can see here the numbers that Copernicus came up with and the actual true numbers are very, very similar. Only Saturn is anywhere close to not just right. So those are pretty darn good numbers. But he did his calculations based on the idea of all of the planets orbiting the sun in circles. So him being able to come up with these radii based on that idea helps to develop some confidence that we're going around the sun. So that is a first line of reasoning there. The second line of reasoning I explained last night. That retrograde motion where normally if you view the position of a planet each night, you'll see from one night to the next that it's slowly progressing eastward in the sky. So every night the planet's just a little farther east compared to the stars than it was the night before. But then you have those periods where it suddenly reverses and starts moving west. So we call that retrograde. It's going backward. And that's explained with his circular orbits simply as we've gotten to the place where the Earth is passing the planet. When the Earth passes the planet for a short period of time, it appears to go backward. And they'll start going forward again. And like, if it's still not clear who can predict what's going to be next Tuesday night? If it's not clear next Tuesday night, we will do a paper drawing and actually seeing how it works with orbits. So this was very simple to explain the retrograde motion, whereas Ptolemy had to have the very complicated epicycles on the deference system. So it was a much simpler explanation. It seemed to explain things great. It wasn't perfect. In fact, it didn't actually give better predictions of the positions of the planets than Ptolemy's model. So I mentioned last night, you have these scientists, they have been completely indoctrinated in the Ptolemaic model, right? They believed it, their professors believed it, their professors' great-great-grandparents believed it. So everybody's just deeply ingrained with this Ptolemaic model, and Copernicus is saying, no, Aristarchus was the one that was right. Everybody's, no, we've already gone through this. Do we have to revisit it every time some quack comes up with the idea? It didn't give any better predictions than Ptolemy's model. Now you might say, but I know Copernicus is right. I've been taught that since I was a child. I've been indoctrinated. The flaw with Copernicus's model was that he said that the planets were doing circles around the sun. It turns out they're not. And because they're not doing circles around the sun, his predictions weren't exactly right. They were pretty close, but not exactly right. And so it was that not exactly right that doomed it to people saying, nah, he's not right. So we had to wait until Johannes Kepler for people to really adopt it. So, to see who was listening, I just changed her answer again. The Copernican system was no more accurate than the Ptolemaic system in predicting the positions of the planets because blank just as in the Ptolemaic system. Are you using a clicker or neither? Okay.
What's the channel again?
33.
3.
33, like the classroom. Okay, everybody's answered. And we have 1, 1, 6, 3. Now go ahead and turn to your neighbor. And if your neighbor answered the same as you, find somebody who answered different so you can get some variation idea and talk about why you answered the way you did.
It's me, isn't it?
Can't be. Can't be you or Russell. Yours and Russell's are sitting in my office right now.
Watch it as not.
Well, me too. Okay. You guys discussed it? Got some confidence? Sure you do. So answer again. Okay, everyone answered the same. So it came up Yari, which I'm sure she was like looking the least confident of everyone. I showed people the card beforehand, and you know it's not based on that. So explain why you came up with your answer.
The second answer?
Yeah, the second.
Okay. Well, I felt persuaded by the people around me. Honestly, that's why. Because like I couldn't remember the universe circulation. So, but after hearing them saying that could be it, because like all the planets, well, we think all the planets orbit around the sun. So we assume that if it wasn't more accurate, it was because it was just circle.
Okay. Everyone's right. This is good. Unlike last night where we all moved toward the wrong answer. Everyone's right. You're right. And the answer that Kepler came up with that convinced people was that Kepler, not Copernicus, came up with elliptical orbits. And that's what we believe the planets are doing. We have plenty of measurements that confirm an elliptical orbit for the planets. And so that was the problem with Copernicus's idea, the circular orbits. But before we talk about Kepler, we have to talk about Tycho Brahe. Now, Tycho Brahe is a very important figure in astronomy, but he's a much more interesting figure in astronomy than he is important in my opinion. So let's go to the next slide. Got some pictures here from Tycho Brahe. So Tycho, there's the gentleman. In this picture, it looks like his nose is complete. Au contraire. He lost this part of his nose in a duel. I always assumed it was with revolvers. It was not. It was a fencing duel. When he was in college, he and another student got in an argument.
Wait, what year was it?
1500s.
Revolver wasn't invented yet.
The what?
Revolver wasn't invented
Yeah,
yet.
who pays attention to when the wrong? Apparently you do. Not me, though.
I don't think the flintlock pistol was invented yet.
Okay, so we have two collegiate aspiring mathematicians, and they're going to class and they just get miffed at each other. And it's not one of those things that you can work out. It's to the point where I take the gauntlet, slap you in the face, and we go out there with the swords and we try to cut each other up. So I don't have a clicker question on this, but what do you suppose their argument was that had to be settled with swords?
You stole my juice box.
You stole my juice box. Close. What did you say, Russ? Over a girl? It's a good answer. It's not right. Max.
Which model was correct?
Which model was correct would be good for astronomy class, but it's not right. They were trying to work out a math problem, and each one said, no, you did it wrong. And that was so serious, they had to go out there with swords to duel. And Tycho apparently lost because he had part of his nose that he lost in that duel. I have never seen.
The problem, right?
I have never seen who was right with the math, and frankly, I wouldn't consider the math that important. See, I don't understand why you go to a duel with a math problem. Okay, but if I had lost a duel because of a math problem, I would probably be a little embarrassed about it. But Tycho, apparently, he was not embarrassed. He was proud. Just like, people put gold rings in their ears or their nose. He had like gold and silver prosthetic nose pieces made so that he could look smart with his, his prosthetic nose there.
So did he really lose that?
I'm going with yes. You would rather have that chunk of cartilage and whatnot. So, interesting fellow. He also became very famous because he observed something that wasn't supposed to happen. If we take as a given the Catholic belief, based on Aristotle, that everything out there is perfect, there was also a corollary to that, maybe I shouldn't speak English either, that perfection doesn't change. If it changes, it can't get more perfect because it was already perfect. And so the change must indicate that it was becoming less perfect. And so the belief was that all of the things out there in the heavens must stay the same, not change. But Tycho Brahe observed, okay, so it wasn't 50-50 because, it wasn't when he was 5, or 4. But, we could add up, say it's about 15, 70, ballpark. He observed a new star. It didn't stay around. It appeared, was there for a while, and then disappeared. So it was named Tycho's Nova, Nova meaning new, and he became very, very famous. So the king of Denmark, who I like to pretend is a relative of mine,
Actually, that might be true. If that is true.
it might be my ancestors that were Venes were Norwegian, and he had the island of Veen in Denmark, so probably not the same Venes. That's what I like to think. But anyway, the king of Denmark set him up with the world's most awesome observatory, the greatest observatory in the world. And this is obviously not a photograph, but a drawing of that world's greatest observatory. Now, if you look, excuse me?
Is that his chair?
If you look at this picture, I'm going to ask you a question that's relevant to what he just said. This picture shows the actual Tycho. It shows his scribe. It shows his jester who was supposed to sleep underneath the table and eat scraps from under the table. When he was dying, he would just give him scraps and kept him entertained. And one other. So where is the real Tycho. One's a picture of Tycho, one's the real picture. Where's the real Tycho in this picture?
Is it a guy in the corner over there?
It's the guy in the corner. This here is supposed to be the real Tycho, and then this here is the drawing that's showing the wise Tycho pointing to something. Now, how does this thing work? This isn't what you tend to think of when you look at an observatory, right? What do you think of when you go to an observatory? Telescopes. Well, telescopes hadn't been invented yet. So if you don't have telescopes, how are you going to observe the sky? Naked eye. So here's what we have. A hole in the wall. And then this here has angles marked for what angle you're looking through the hole in the wall. And this seat can be moved so you can sit different places and look at different angles. And so he would sit there and observe through a little hole there, so he's lined up and getting a nice angle, and observe when stars pass the window, and they would record the time and angle for the stars each night, the planets. Now I think of that and I think, wow, the tedium. Not for me. But that's what he was doing, and he made the world's best observations of the sky from this observatory. Hence, the reason he's famous. Well, in astronomy, the reason he's important. He made the world's best observations. He had the world's best observatory. Now, other things about his life, he was apparently not a kind ruler to the people, but he did run an efficient city. He went to eat with the king one night, and he fell sick. Now, I had always been taught when I was younger that he fell sick because he drank too much and he had to go to the bathroom, but it would be impolite to stand up in the presence of the king, so he remained seated and his bladder ruptured. One of my kind pre-med students point out, okay, that's not physically possible. You cannot hold it in enough to rupture your bladder. But what is known and what is factual for sure is that he collapsed and he was ill for about 8 days before he died. And during that 8-day period, he made it clear that he wanted his laboratory and his data to go to his assistant that he had recently hired, Johannes Kepler. Well, he died, and his family, wealthy people, said, Johannes Kepler isn't getting this. This belongs to our family. And so there was a long, protracted legal battle. And eventually what happened was Johannes Kepler snuck out the data and let them have everything else, and kind of stole the data. I say stole because in the courts, I believe the courts ruled with the wealthy family, and he wanted that data. Now, as we'll see in just a moment, Johannes Kepler was an undeniable genius. Also a little weird, but an undeniable genius. He caught the attention of Tycho Brahe with things like this. This here is an idea he came up with, that you could use regular geometric shapes to space out the planets in the solar system. And so you have this regular geometric shape, and then you have a sphere that fits just around it. The thickness of the sphere you can see there is the epicycle width, and then you have the next geometric shape. It's really ingenious. As far as anyone knows, has no connection to any physics reason, but it's very ingenious, and that's what attracted him to Tycho Brahe. So Johannes Kepler, he graduated from college, got a job as a teacher. As a teacher, you really have one important job, and that is helping your students learn. That's what I'm hoping to do as I sit up here and yam rant. I want you guys to learn about astronomy and to enjoy it. Well, he got his job as a teacher, and after the first year, no one signed up for his classes. He was just that good. But he was hired away after a year or two of teaching. They readjusted his schedule, forced people to take classes from him, and started working for Tycho Brahe. Now, Tycho Brahe was trying to develop a revised version of the Ptolemaic model. And it was a pretty convoluted model. We're not going to talk about Tycho's model at all. He was trying to come up with a new model. And Johannes Kepler, when he took Tycho's data, he wanted to use that data to finish Tycho's work, to finish Tycho's model. But in analyzing the data, he saw a pattern. And as far as I understand, the test of a genius is recognizing patterns. He recognized a pattern that no one before had ever recognized. And so the first thing that he recognized is the data for the positions of the planets each night is not consistent with circular orbits around the sun. It's consistent with elliptical orbits around the sun, with elongated circles, if you will. And so he came up with 3 laws, Kepler's 3 laws, surprisingly enough, to describe them. So the first one is that all of the planets orbit the sun in elliptical orbits with the sun at one of the 2 focal points of the ellipse. Now I say one of the 2 focal points of the ellipse, and most people who aren't mathematically trained are going to say, okay, so what in the world do you mean by one of the 2 focal points? Well, if you have a circle, the circle has one center, clearly enough. To make an ellipse, you basically split the center out, and so you have 2 focal points, and it goes around those 2 focal points. And when I switch over to the Java app, you'll be able to see more clearly what's going on with those 2 focal points. But he said one of those focal points is going to be the sun. The other one's just an empty spot. And so we'll talk about the properties of an ellipse when I go to the applet. That's the first thing. Elliptical orbits with the sun is one of the focal points. The second thing was, well, this I'm going to talk about the other. The second law was that as the planet goes around, the area of a line that goes from the sun to the planet, the area it sweeps in a given amount of time is always the same. So like in 1 month's time, if you were to take a line going from the sun to the earth, and you measure the area swept out by the line connecting those 2, and then you wait some other time to do it again, you'd have the same exact area. Now we're not doing geometry calculations here. So I have a very simple take home for you for Kepler's second law. What that means is when you have a shorter radius, that's when it's closer to the sun, to sweep out the same area, it's going to have to go faster. So for a given planet, when it's closer to the sun, it moves faster. When it's farther from the sun, it goes more slowly. So they don't have a constant speed as they orbit the sun. Yeah.
I'm assuming, do people know why that is? Is it has something to do with when they're closer to the sun, the gravity pulls it faster around the...
It does indeed. At the time of Kepler, nobody knew why. But then we had Sir Isaac Newton come along. We'll have him, I don't think we'll have him today, I think we'll have him Friday. And he came up with his calculus and his law of universal, well, we will have a law of universal gravitation today, so I guess we could have him today. And his laws, Newton's 3 laws, and those together gave physics reasons for Kepler's laws, including this one here. The pull of gravity gives it more kinetic energy as it comes in, which means it's going to go faster. So yeah, we do know why, but at that time they didn't know why. It was just an observation. Now the third law is up here. The third law is a very easy to put into math relationship that says the period, which is the time for one orbit, squared is proportional to the average radius cubed. And if you use Earth units, so period in, what's the time it takes for the Earth to do one orbit? What's the unit that's just one? It takes one blank for the Earth to go around the sun once.
1 year.
1 year. So if you use your time in units of years, and you use your average radius in the unit that is the average distance between the Earth and the sun, what's that unit? The astronomical unit. Then it's just an equal sign. The period squared in years is equal to the average radius in astronomical units cubed. So that's his third law. So now I'm going to go to this website that's shown right here. And we have a planetary orbit simulator. So you can see there, this is actually set to be on Mercury. I have my animation rate, so it's moving pretty quickly. If you look at that orbit of Mercury, you can see that's not a circle, is it? It's stretched out. In fact, I can show the empty focus. There's the other focal point. And of course, clearly enough, the center is halfway between the two. Now we have some nomenclature things here. We have, for ellipses, the major axis and the minor axis. The major axis is the longest line that goes through the center from edge to edge. So that's the major axis, the long axis. The minor axis is the shortest line that goes through the center from edge to edge. Semi means half. So this shows the semi-major axis, that's half of the longest line, and the semi-minor axis, half of the shortest line. Those are actually important numbers because we use them to describe the shape of an ellipse. Or we can take those numbers and combine them and get another set of numbers, which is the eccentricity. See over here we have the word eccentricity. You see where I'm hovering? The eccentricity. The eccentricity is telling you how elongated it is. So this is Mercury right now. It has an eccentricity of 0.14. If I lower that eccentricity to 0, that's the animation rate. Whoops, that's not an eccentricity of 1.1, eccentricity 0.206. If I lower the eccentricity to 0, it's a perfect circle. It's no longer Mercury, right? And this allows me to change the eccentricity out to 0.7. 0.7 is not a theoretical limit. It's just a number that this is limited at. But you see at 0.7, it's very much elongated. And you see the sun would be very close to the planet on the one side, very far on the other. Get rid of some of these things. Here, those green lines are the radial lines. Let me slow it down a bit. Those lines are a line going from one focus to the planet to the other focus. One of the rules about ellipses is that the sum of those two lines is always the same for an ellipse. So as I like to say, if I am stranded on a desert island, and for some reason I need to draw an ellipse in the ground, I don't know what that reason would be, all I have to do is, make myself some string from the palm leaves and put two stakes in the ground, tie one end of the string to one stake, one end of the string to the other, and then just go around and keep both the string tight, and the shape that it allows me to go around will be an ellipse. Or to put it in more practical terms, you can take a piece of string and two pins, tie the string so it has a loop that each pin goes through, put it down on paper, and then just keep that string tight and bring your pencil around, and you'll draw an ellipse. So it's simple to draw an ellipse with, of course it's also simple to draw a circle. Circle, you just have one pin, and the string goes constant length. So that's what these green lines are to indicate. You can see, well, you can't see, hide it. You can see at the bottom, it says the length of each of those two strings and the total remains constant as it goes around. So that's about the shape of the ellipse. The eccentricity tells us how circular or not. Eccentricity of 0, perfectly circular. Eccentricity of 1 would mean it's going in a straight line back and forth. That's the theoretical limit. This just only goes to 0.7. So I'm going to go back to Mercury here. Something that's like a planet. Let's go to the simulation of the second law. So the second law says the area swept out per unit time is always the same. So, okay, I'm going to change to larger eccentricity. The larger the eccentricity, the clearer this becomes. This does a sweep for 1/16 of a second here. So I'm going to do a sweep for 1/16 of a second when it's close to the sun and when it's far from the sun. The area that is in, I don't know what to call that, puke color, is the same as the area that's in burgundy. But in order to have the same areas, you can see the distance that it moved for the burgundy part was a small distance compared to the distance it moved for the puke color, much larger distance, to get the same areas. Now, there are mathematical relationships for this, but all that I care for you to remember for the second law is that a planet moves faster when it's closer to the sun, slower when it's farther away. Okay, the third law, the animation here is just really lame. If you change the size of the orbit, if you look at the picture down here, the graph, it's moving up and down on that graph. It's pretty hard to illustrate that law. But the law says that things that are farther away from the sun have a longer period, a longer time to do an orbit. So one can immediately say, okay, the closest planet to the sun, Mercury, has the shortest year. And they get longer as we go out, so Neptune has the longest year of all the planets. And Pluto, not a planet, farther out, has a longer year. Eris, farther out, has an even longer year. Next.
How long is Neptune's year?
I don't know. I know Uranus is 84, because I graduated in 1984 from high school. It's easy to do. Neptune's is longer than 84 years. That's all I can say offhand. I had to tell you that I know something, but I'm not completely ignorant. Yeah. Sorry, I don't know the answer. The last thing this has is Newtonian features, which we're not going to worry about. So any questions about this animation? I think it's really cool, very instructional, hence I spend time on it. You guys have any questions about it? If you want to study this on your own time, there's the link for it there. Okay, next clicker question. Uh-oh. I don't have that question on my clicker. Somehow I deleted it, which means that you can't actually answer it. So, since you can't actually answer it with your clicker, I know, it's so disappointing. What I can do is just say, okay, which one was the take home I wanted you to get from Kepler's second law? I heard one. I'm going to circle it and then read it. A planet should move at its greatest speed when it is closest to the sun. That's right. That's the take home that I want you to get for the second law. The first law, the planets are orbiting in ellipses with the sun at one of the focal points. The second law, the planets are going fastest when they're closest to the sun. The third law was that the period in years squared is equal to the average radius in astronomical units cubed. Actually, going back to this animation, I said the average radius. The average radius is the semi-major axis. So when we use that A, we mean the semi-major axis. Now, you might ask, how could that be the average radius? I mean, that's the largest distance from the center to the edge. So how could that be the average radius? Because the radius would be measured from the sun. And so measuring from the sun, this is I can't draw on this one. It's the shortest over here and the longest on the other side. And the average that it has is that semi-major axis. And so we use the semi-major axis. The true word that you should use here is the semi-major axis cubed. But for a class like this, when you're just learning, you've never heard of semi-major axis before today probably, right? So it's good to get that average radius idea tied in so you know what you're talking about. Okay, Galileo Galilei. I'm probably going to have to end with him given that we only have 6 minutes left. I like to say both of his names just because of the repetitive sounds here. He's often considered like the father of science because he's the one who really pushed the idea that we have to test our ideas. We shouldn't just say, oh, that's a beautiful idea. It must be true. But we should do some experiments and test them. So developing that scientific method of coming up with a hypothesis to explain why something happens and then testing the predictions of that hypothesis. And he did lots of testing of his theories. He was also, by the way, a very haughty man. One of the things he loved to do was tell people, you're wrong! And that led to his eventual demise, as you may or may not know the story, but I will relate it. Some people believe that Galileo invented the telescope. Not true. The telescope, we don't know what person to credit for it, But we do know that it was people from the Netherlands who invented the telescope. Now they invented the telescope, two lenses, as a party game. The idea was, look through this, see the awesome things you see? It's like a kaleidoscope, but better. And Galileo heard that these merchants were selling this cool device, and he got the idea, I could use that for systematic study of the skies, not just for parties. So he went to try to buy one from them. They were gone. He heard people's descriptions of them. He developed his own telescope and improved the telescope. So he improved telescopes. We still to this day use telescopes we call Galilean telescopes that are to his design. But he didn't invent the telescope. And he used it to carefully look at the skies. So here's an actual reproduction, I think that's a photocopy, of his notes from observing Jupiter from one night to the next. Obviously, the typing there is not part of the photocopy, in case anyone's, I think he's pulling my leg. But what he did is he wrote, here's Jupiter, and I see these things through the telescope that are, close to Jupiter. And then when he looked at it just the next night, there was considerable change in position. And so he kept observing them. Of course, you see January 9, he skipped. Kept observing them and saw that these moved around. He said, those must be like our moon orbiting around Jupiter. This was heresy, because the Catholic Church had established that everything up there is heaven, here's earth, and everything below is hell. Everything has to go around hell. And if everything goes around hell, and we have here something that's going around Jupiter that's not hell, then we got ourselves a problem. So he found something that violated the Catholic belief here. Something he was pleased with. He also saw the rings of Saturn, the first person to ever see the rings of Saturn. This picture in the bottom right is to illustrate the true quality of his telescope. He probably just saw something that looks more like that, a circle with some blobs on the sides. But he recognized there's something funky going on here with Saturn. He also turned his gaze upon the sun. Now, next year, August 21, we're going to have that solar eclipse, the Great American Eclipse. Do not go out and look at the sun with your naked eye. When it's fully eclipsed, you take your glasses off and look at the sun. But as soon as the sun reemerges, put them on, because the sun will hurt your eye. Question?
How did you do the binocular? How did you do the binocular?
Oh, he damaged his vision. Yeah, that's why you don't want to do it, right? But he observed that the sun was not perfect, that the sun had flaws, dark spots that would come and go. And he observed that, he could see that they rotated as he, observed day to day. And
dark spots just kept staring.
yeah, true enough. Now, we know that the moon's surface is not nice and perfect, right? And people had explained that away. Said, okay, the earth is imperfect. The earth has sin. And the moon is so close to the earth that the earth's sin has marred the surface of the moon. So they had an explanation for why the moon had craters on it. Or, what they didn't know for certain, craters. But this was too far away. And they're like, how could it be? How could we have flaws on the sun that should be perfect? Another thing that he discovered was looking at the phases of the inferior planets, like Venus. Venus, if it was going around the Earth, and the sun was going around the Earth, you could have times when Venus and Earth are opposite each other, and you should be able to see a full Venus. But if you have the Ptolemaic model, okay, so the Copernican model or the original Aristotelian would allow for a full Venus. But with the Ptolemaic model where Venus is pegged to a line going from the sun to the earth, which is a way to make it so it didn't have an elongation of greater than 47 degrees, or 48 degrees, I guess. 40, it's one of those two numbers. You couldn't explain having a full Venus. And so he observed a full Venus in his telescope. All of these things said the earth can't be the center. Now, I want to show you this picture. Don't worry about answering the question. We'll answer the question next class period. This picture shows the Ptolemaic model with a line going from Earth to the sun, and then the epicycles for Mercury and Venus locked onto that line, so that you never have large elongations for them. I do want to finish. I know I'm at my limit. We know that Galileo, in the end, had to recant, saying that the Earth was not the center of the universe. But the story behind that is very interesting. His buddy was a cardinal. They were tight. And he came up with these ideas. He liked to talk with them, with his buddy. And then his buddy became the Pope. And so when his buddy's the Pope, he's all, hey, can I write a book that explains my ideas that I know you guys think are heresy? And the Pope says, yeah, as long as you make sure you put in not just your ideas, but also the church's ideas, right? We don't want you to be indoctrinating people. We want you to give both sides a balanced approach. And so he writes this book. It's printed with the official imprinter of the Roman Catholic Church. It's proved. And the book, which we call in English like dialogues, it's dialogue between three people, one that's very wise, one that's an idiot, and one that makes good judgments. And so the very wise person explains why the earth goes around the sun. And the idiot, his name is Simplicio, or simpleton, explains why the sun goes around the earth. And then the person who can judge, has good judgment, says, I can see that the wise man was correct, the simple man was wrong. So basically what he was doing is he was putting all of the wrong arguments in the Pope, the Pope's arguments in the simpleton's mouth, and mocking the Pope in his book. And so when it was pointed out to the Pope that you're being mocked in this book that you've approved, that's when all the heck came down on him and he was forced to recant.
That's a way to treat a friend.
Yeah, it really is. Okay, have a great day, and I'll see y'all on Friday. Remember, homework is due tonight if you turn it on paper by 5 at my office. If you turn it in online,